Okay, now once you know the Gibbs function for a particular, or Gibbs free energy or Gibbs function for a particular species I, then the mixture, the Gibbs free energy of a mixture of ideal gases can be calculated by just same thing like Ni into, say when I say H, it is sigma Ni Hi, that is all here. Same thing I am using here, sigma Ni, instead of just say this is number of moles of ith species into Gi, but calculate at a particular temperature and pressure. So that you can now you expand this term here and write. So sigma Ni times Gi of T comma P naught plus RUT natural log of Pi by P naught. So this is the Gibbs function at a particular temperature calculated atmospheric pressure. Okay, again we have tables for this, and this you can calculate knowing the mole fraction of the particular species. Okay, in fact, if you want to determine mole fraction, this term is going to be useful for us. Okay, so now this is the equation, G mix is equal to sigma Ni times Gi of T comma P naught plus RUT times natural logarithm of Pi by P naught. Now the condition for equilibrium at a given temperature and pressure is dG mix equal to 0, and this you have to just differentiate this by chain rule. So dNi G plus Ni dG, okay, dNi G plus Ni into dG I am put. So I put here. So now you can see that the second term here goes to 0 because at a given temperature, okay, G has a constant value. Similarly, pressure is constant, partial pressure is dependent on the total pressure, that is constant. When you sigma for all the partial pressure, you get total pressure, and total pressure is held constant. So this term, second term goes to 0. So that means dG mix will be just equal to the first term. Okay, so that means the condition for equilibrium is dG mix equal to this sigma I dNi times Gi of T comma P naught plus RUT of natural logarithm of Pi by P naught, that should be equal to 0. So that is the condition for equilibrium. Okay, now this has to be implemented in the for any reaction. So for example, when I said equilibrium reactions, I considered CO2 giving CO plus half O2. Similarly, H2O, any equation you can take, H2 plus half O2. So these are all equilibrium reactions. So I have to apply this condition to the equilibrium reaction to get the equilibrium products. Okay. So now let us consider elementary reaction which are reversible in nature. See this, these are reversible in nature. Okay. So now let us consider a arbitrary elementary reaction written like this. Capital A, B, C, D represent the species, and the small a, b, c, d represent the stoichiometric coefficients. So small a times capital A plus small b times capital B, reversibly giving small c times capital C plus small d times capital D. That is the general equation we are trying to consider here. So we can also have, say, equation like this. So we can A, B, C, D, etc. We can have equation like this by molecular reactions. So now you get any general equation like this, written like this. Now try to apply this condition and see how to evaluate this. So before going to the this evaluation, we should understand what is the change in the number of moles, dNi. Okay. So the change in the number of moles of a species is directly proportional to the corresponding stoichiometric coefficient, correct? So if A for the species A, if A small a is the stoichiometric coefficient, then the change in number of moles of the species A will be proportional to stoichiometric coefficient. Okay, so I add a constant of proportionality K. Okay, I also put a minus sign here because that is a reactant. So we definitely know that if we consider forward reaction here, okay, then the reactants are consumed. So dNA and dNB should be negative. So I put a negative sign. And the change in the number of moles is proportional to the corresponding stoichiometric coefficients A, B, etc. here. So I put a proportionality constant K. Okay. Okay, coming to the products, similarly the change in number of products will be correspondingly proportional to their coefficients here. So, D and C will be proportional to C, D and D will be proportional to small d, and I put a plus sign because they are produced in the forward reaction, and the constant of proportionality is K. Okay. So, this is the way. So, you can now replace dn's by K times A, K times B, etc. for the particular reaction here. Put with the sign you have to put. So, minus for the reactant, plus for the product. Okay. And when I consider the reverse reaction, then D and A will be positive, D and B will be positive. On the other hand, D and C and D and D will be negative when we consider reverse reaction. So, the Kb value, etc. what we are going to calculate next will be dependent on which direction you consider the reaction. Okay. Now, let us apply the this rule DG mix, calculate DG mix for the reaction, and this is what when I make it equal to 0, then I get this. Okay. A. So, K cancels out, A into G of A at a particular temperature T and pressure, atmospheric pressure, plus RUT times natural logarithm of partial pressure of A by P naught, plus B times GB of this temperature, given temperature, and P naught, plus RUT of natural logarithm of PB by P naught, that is equal to the C and D's, correct. So, the product C is the coefficient of the species C, that into GC of T comma P naught plus RU T natural logarithm of partial pressure of C by P naught. Similarly, D, you can add this. So, this is the equation I get when I subject this equation to D mix equal to 0. Now, you try to group the Gibbs functions in one side and the partial pressures, these partial pressures PC, etc. in the other side, okay, like this. So, I now group this in one side and take the partial pressure on the other side. So, minus C GC of T comma P naught plus D GD of T comma P naught minus A. So, minus of minus I am putting. So, minus A GA of T minus P naught T comma P naught minus B GB of T will be equal to, now group this log terms, RUT times logarithm of the product, partial pressure of product raised to the coefficient, the stoichiometric coefficient. Okay. So, PC by P naught power C, small c, PD by P naught power small d divided by the reactants, again same products, product of the reactant partial pressures, PA by P naught power small a, which is the stoichiometric coefficient, multiplied by PB by P naught power b. So, this term we get. So, this is the equation what we get, and I am grouping the G's in one side, partial pressure terms in the other side, and get this equation. Okay. So, now I started from this equation, applied dG mix equal to 0, I got this equation, and I grouped the G's in one side like this, left hand side, and the partial pressures in the right hand side, I get this equation. Now, I define the left hand side as standard state Gibbs function change delta G at T comma P naught. So, delta G at T comma P naught, so you can see in the Terns book, this is represented by this in a compact notation, delta G superscript 0, that is for standard pressure, atmospheric pressure, and the subscript T represent any temperature. So, I have just written delta G T comma P naught, you can also write like this, delta G superscript 0 subscript T, that will be equal to, now group the products, okay, Gibbs energy of the products, C coefficient, stoichiometric coefficient, GC of T comma P naught plus D, stoichiometric coefficient of D, capital D, GD of T comma P naught, then minus, you can add the reactant sides, same thing. So, all the product Gibbs free energy multiplied by stoichiometric coefficient should be added, and that should be subtracted to this reactant, again the sum of reactant this. So, this is the Gibbs function change, standard state Gibbs function change, calculated at any temperature, but only at atmospheric pressure. So, that means delta G is a function of function of temperature only. Delta G is a function of temperature only. Now, in the right hand side, I have already grouped the partial pressures like this in the natural logarithm term, correct? Now, that I define as equilibrium constant based on partial pressures. Okay. Now, this partial pressure is the ratio of product of the partial pressures of products, okay, raised to the stoichiometric coefficient divided by corresponding atmospheric pressure. Similarly, that divided by the product of the reactant partial pressure ratios raised to corresponding stoichiometric proportions. So, this partial pressure ratios, okay, products multiplied of multiplication of all the products divided by the product of all the reactants, that ratio is called the equilibrium constant at partial pressure Kp. Okay. So, now I can write the previous equation, this big equation I can write. So, this equation, okay, I can write like this: delta G T comma P naught equal to minus RUT natural logarithm of Kp, which is this ratio, correct. So, this ratio, this Kp is this. So, now you please understand that to calculate Kp I need this. So, temperature is known already. So, since temperature is known, delta G can be calculated because delta G is a function of temperature only. It is done at atmospheric pressure. So, this is known. When temperature is known, this is known. So, then Kp can be calculated. So, Kp also is a function of temperature only. Okay. So, that is what I am doing here, calculate Kp as a function of temperature only. Now, how the pressure effects come? Because of the definition of Kp, pressure effect comes here. So, partial pressure are involved. So, partial pressures of products, they are multiplied together with the ratio with atmospheric pressure raised to corresponding stoichiometric proportions, and that divided by the product of the partial pressure ratio of the reactants raised to corresponding stoichiometric proportions. So, this definition, the partial pressure itself Pc, Pd, Pa, Pb will change based upon the total pressure. So, the pressure dependence comes by the definition of Kp. Kp itself is calculated as a function of temperature here, and you can substitute the value of Kp in this to get the product composition. Okay. So, in terms of H and S, Kp can be written like this. So, if you do not want to use G, you can also use H and S and do this. Both are same only basically. Okay. Now, so to summarize, you know that the Gibbs function change is a function of temperature only. So, Kp is also a function of temperature only. Okay. Now, after calculating Kp like this as a function of temperature, you can use this equation. So, what I have done here is I have just put see, instead of Pc, I am putting Xc times P. Similarly, Pd, I am writing Xd into P. Okay, and substitute here this equation here. When you substitute for Pc, Xc into P, similarly for Pb, Xb into P, etc., you can write in terms of mole fractions and the total pressure P. So, after evaluating Kp at a given temperature with the Gibbs function change, standard Gibbs function change, then you can calculate this, substitute this to calculate the or to generate expressions. You cannot calculate everything. So, if it is only one unknown, this only one equation can be used to do that, or if there are multiple equations, you have to generate equations in order to solve. For the mole fractions, mole fractions can be written in terms of the number of moles of a particular species. So, for example, mole fraction of C can be Nc divided by N total, or Np I will say, that is the number of moles of the product Np, Nc is the number of moles of the C. So, Xc will be this. So, when you substitute, you can also substitute this equation in terms of number of moles, correct. So, straight away you can write the equation in terms of number of moles A, B, C, D, E, what we saw earlier. So, once you do that, we can calculate. So, the procedure of calculating the equilibrium product is, first you find the Gibbs free energy of individual species, then calculate the standard Gibbs function change at a given temperature at the reference pressure of 1 atmosphere. So delta G is got. Then you calculate the value of Kp using this expression. Then substitute this for the given equation and find the number of moles, or form an equation with the number of moles involved. Okay. So let us just take the equation what we considered, in which we have some CO2 dissociation taking place. The equation is CO2 reversibly giving CO plus half O2. Correct. So now in this case we know that the mixture has 1 minus alpha kilomole of CO2, alpha kilomoles of CO and alpha by 2 kilomoles of O2 at a given temperature. Now we can calculate delta G at atmospheric pressure as GCO product. First of all, you have to group the products. So these are the products, these two are the products. So GCO at a particular temperature, then 0.5 times GO2 at a particular temperature, calculate them, add up. Then reactant GCO2 at the same temperature you calculate, then subtract that to this. Now you get delta G. When delta G is known, calculate Kp. Kp is exponent of minus delta G by RUT. Okay. So you can write in a compact form like this. Okay. So this is the expression you make. Then use definition. Okay, what is the definition here for Kp? Kp for this equation, Kp is written as partial pressure of product first of all. So partial pressure of CO by P naught power 1, then partial pressure of O2 by P naught power half divided by partial pressure of CO2 by P naught power 1. Okay. Now if the pressure of the reaction is P, total pressure, if P equal to total pressure, then PCO will be equal to XCO times P. Similarly, you can write X O2 into P as PO2, and PCO2 will be equal to XCO2 into P. So substitute this here, these partial pressures here, you get this equation. Then what is mole fraction? Total number of moles, equal to 1 minus alpha plus alpha by 2, which is equal to 1 plus alpha by 2. So XCO will be equal to alpha by 1 plus alpha by 2. Similarly, you can substitute for other things, and you can write this in terms of alpha. So alpha by 1 plus alpha by 2 is the XCO. XO2 is alpha by 2 divided by 1 plus alpha by 2 power 0.5. Similarly, number of moles of CO2 is 1 minus alpha divided by total number of moles 1 plus alpha by 2. So that if you write, then you get a non-linear equation in alpha. So Kp is known. Right hand side alpha in a non-linear form is there. So you know the total pressure is known. So this pressure ratio can be calculated. So you get a non-linear equation involving alpha. Solve that. Okay, a non-linear equation results. So if you are solving, you get the value of alpha. So it's only one unknown, so one equation is enough. Okay, but non-linear equation will give multiple roots. You have to choose physically possible roots. That's all. That will be the value of alpha. Okay, so we know that the Gibbs function change is a function of temperature only. So Kp is a function of temperature only. So the temperature dependence on the products of equilibrium comes due to that. The pressure dependence comes due to the mole fraction and this pressure term here. So that with that we take into account both the effects of pressure and temperature and calculate the equilibrium value of a particular species. Okay, now some observations. When pressure increases at a constant temperature, the backward reaction is favored. Okay, dissociation normally occurs at high temperatures at atmospheric pressure. When pressure increases, then there is a decrease in the dissociation. Okay, now adiabatic flame temperature when you calculate, by calculating the equilibrium products of combustion, then that value is close to the measured value. So such a temperature is called equilibrium flame temperature. Again, as I told you, it has to be determined iteratively. Okay, so this is the completion of this particular topic. If you see in this particular section, we have actually dealt with this. So, we have seen how to calculate heat, temperature, adiabatic flame temperature iteratively. So, heat calculation requires enthalpy calculations of individual species, absolute enthalpy, then calculate the reactant enthalpy and the product enthalpy, apply first law, which is constant volume process, it is the heat of reaction is UP minus UR, and if it is a constant pressure process, the HP minus HR is the heat of reaction. Then the flame temperature you calculate based upon some iterative procedure, but for which you need composition of the products. Okay. So, the adiabatic flame temperature, if this is the maximum temperature attainable when the product enthalpy matches the reactant enthalpy for a constant pressure system, or the product internal energy matches the reactant internal energy for a constant volume system. Okay. Now, composition of the products in equilibrium is determined using second law. A variable defined using second law is entropy. So, based on entropy, two free energies have been defined. One is Helmholtz free energy and one is Gibbs free energy, used in constant volume and constant pressure processes respectively. So, using that we calculate the Gibbs function change, and from that we calculate the equilibrium constant, which is defined as a ratio of partial pressures of product mixture and the reactor mixture, and from that you calculate the equilibrium composition. Okay. So, this finishes this topic. Now, we go for worked examples. Okay. Now, this worked example is corresponding to the heat, temperature and equilibrium calculations. So, this is the thing. So, let us do some simple examples first. So, let us consider the first problem. Ethanol C2H5OH is burnt in a furnace with an equation of 1.1, and the exhaust gas analysis specifies that there is no hydrogen or oxygen left in the exhaust gas. Okay. Now, for a constant pressure process, how to, you have to determine the standard heat of combustion per kg of fuel. Okay. Now, the standard heat of formation of ethanol is given here, that you can use. That is the problem. So, ethanol stoichiometric combustion is written here, C2H5OH plus 3 times O2 plus 3.76 N2, giving 3 times H2O, 2 times CO2 plus 11.28 kilomoles of N2. Okay. Now, actual combustion occurs at an equation ratio of 1.1. So, you rewrite the equation for the actual combustion by replacing 3 by 1.1, and it is given that no hydrogen or oxygen is left. You already seen this in the previous worked example. So, hydrogen combusts fully to H2O because it is highly reactive. However, the remaining oxygen is shared to form CO2 and CO. Now, by incurring C and O balances, you get two equations involving A and B, by solving which you get A equal to 1.4546 and B equal to 0.5454, and the products are this. So, now we can write the equation. So, now product composition is known, this is reactant. So, you can find the standard heat of combustion. Okay. Now, the entire equation is written here with 1 kilomole of ethanol plus 3 by 1.11 into the air, 4.676 kilomoles of our air, giving 3 kilomoles of water vapor, 1.4546 kilomoles of CO2, 0.5454 kilomoles of CO, and 10.2545 kilomoles of nitrogen. Now, standard heat of combustion, okay, delta Hc is nothing but minus of delta Hr, which is nothing but minus of Hp minus Hr. So, which is written as Hr minus Hp. Okay. So, that is the standard heat of combustion. Now, when I say standard, this has to be evaluated at 298 Kelvin. All the enthalpies have to be evaluated at 298 Kelvin. So, only heat of formation of species are involved in this. Okay. So, now for example, HR, the reactant mixture contains ethanol, O2 and N2. However, since O2 and N2 are basic elements, heat of formation of them are 0. So, the HR is contributed only by the heat of formation of ethanol, which is given as minus 235,310 kilojoule per kilomole. Okay? So, that is the enthalpy of reaction. Then what is the enthalpy of products? Enthalpy of product is nothing but sigma. Enthalpy of product is nothing but sigma Ni Hi. Okay. Now, since we are talking about 298 Kelvin, this is Ni into HFI, heat of formation, that is it. Okay. So, now that is what we are trying to do here. 3 times, this is the enthalpy of formation of H2O, and 1.4546 times, this is the enthalpy of formation of CO2 plus 0.5454 times enthalpy of formation of CO plus 0, that is 0. There is no enthalpy formation of nitrogen because it is a naturally occurring species. So, when you do HR minus HP, you will get a positive delta Hc value because it is an exothermic reaction. So, 112296 kilojoule per kilomole of fuel. So, that is this. But per kg of fuel, if you want, then divide by the molecular weight of fuel, you will get 24412.3 kilojoules per kg. So, this is the simple example where you try to find the calorific value or heat of combustion at standard state when there is a slightly rich mixture of ethanol and air reacting.